look at 4, which is the application of control system. So we previously discussed the open loop control system and the closed loop. We can now list some of the application of open loop control system and the closed loop, and later on we will describe how each of them operate. So I can list some open loop. 1, washing machine. 2, we can say a toaster, the traffic light, the volume control, we can say the electric bulb. For the closed loop, we can say the thermostat. 2, maybe the fridge. 3, we can have the adaptive cruise control, sometimes they call ACC. 4, we can have the battery charger, and 5, we can have the smart grid. So those are some of the few I can name for the application of the control system. In the open loop, when we describe each of these control system based on the transfer function, or especially the block diagram, we can see that for the open loop, we only use it when the system is predictable. That means we can be able to predict the response of this particular system. And we have cost and simplicity. When cost and simplicity is more than the precision, and we can have no disturbance. When we have such condition, we normally choose the open loop. We only use an open loop system when this requirement exists. However, in the closed loop, we normally choose a closed loop, and when to use the closed loop when we have conditions such as the precision or the accuracy of the system is mostly intended, and when we have some external disturbance to deal with, and when we have automation and reliability as our requirement. That is when we choose a closed loop control system for our design. Let's look at the first one, the washing machine. So we normally know what is a washing machine. A washing machine is used to wash the clothes. In an open loop, we say we have an input to the controller and to the plant or process, and we have the output. So when you see under open loop, all of these systems should have this basic component, and we also describe each of these components in our previous video. The link for the previous video is given in the description below. If you have time, you can go back and watch our previous video. And we have the washing machine that is given like this, and you have some dial which control the operation of this washing machine. When we have the input to the system, the input normally comes from a timer, and you have operations such as washing and drying. Those can be regarded as the two main operation of a particular washing machine. The input. The input is now the timer based on the operation, which is either washing or drying. And in terms of the controller, so a controller is a circuit that regulates the plant. So we can have the circuit and the plant is the motor, and the output will be washing or the drying. And this input is from the knob that you can see physically on the washing machine. Therefore, if we select the option washing and then we set the timer from the knob, let's say 5 minutes for washing, then this information will be transferred to the controller. So a controller is a circuit that regulates the input. Based on the input or the reference value of the input, the controller will perform accordingly. According to the timer which is inbuilt in the circuit, when the option of washing is pressed, then the circuit with the timer will regulate the washing for 5 minutes. Let us look closely to the controller. How can someone design a controller that can be responsible for such operation? We have the input and we can have the timer and we can have a relay. So upon the input, we receive a command that the time should be 5 minutes and the option is washing. When this input is now selected, what will happen? This timer is now responsible for regulating the time. It will capture the time countdown and the washing option will be guarded by the relay. When the relay is closed, if this condition is true, the relay will be switched on, and this relay is now connected to a power supply that drives the motor, and the motor is now responsible for spinning the mechanism that guides the washing process. So during the process, when the timer count down from 5 to 0, that means the timer will now send the signal to the relay to turn off. When it turns off, that means the motor will stop. So it won't be able to continue the washing process. From such open loop system, we can see that the output is mostly predictable and we don't care how the machine wash the clothes, so long as we have the clothes perfectly washed. And within that process, we don't care about the precision because the clothes is not too important. And we can see from this diagram, it is mostly simplicity, meaning this type of design is simple. And we disregard the disturbance such as the alignment of the washing machine, how fast, how speed, or if there is any fluctuation with the power. We don't really care about this. All we care is we set the timer and the washing. And once these conditions are set and it is done, then we don't care about any of the other operation. This is one of the simple example in which we can identify the open loop. Another example can be the toaster. So in a toaster, we have the controller and the plant. The plant is nothing but the heating element. And the controller is a small circuit that will regulate the input. So apart from the washing machine, we can identify a toaster we have the slot and a toaster and a knob, or sometimes we have a button that we can press. And this knob we can select option such as low to high. For low toasting we can select the low to low, and for the high toasting we can select the option high. Then we normally press the switch downward, and according to the timing of the low we can say 1 minute, and maybe for the high we can say 3 minutes. Therefore the input we can say the knob, which represent either it is high or low selection, and the other one is the press. The press, when we press the switch, it will now start the toasting process. We can simply look at the schematic. We have, for example, the switch. When the switch is pressed, it is connected to, if we have a 555 timer. So this timer is responsible for regulating the minutes. And we have the heating element. With the input of the switch, when the switch is pressed, then there will be a counter timing on the LM555 timer or any 555 timer to continue the heating element. So once the timing is done, if we select, for example, low, then after 1 minute, then this push button will be released. And now it will be in the upward direction and the heating will be stopped, because we don't really need the accuracy, and also we are not concerning about the reliability of how this toaster will operate. In the case, it won't care how the bread will be prepared afterwards, whether the bread will bend to an extreme or it will be bent in a limited version. This particular toaster does not care. Therefore, there are no feedback from the output, which is the bread itself. All it cares about is to follow the input. Whatever direction the input receive, it will produce the output, and no feedback is required in a case where no precision is required. And this is also one of the simple example that we can identify. If you have a toaster at your home, you can try observe what is really happening based on this explanation. Now let us look at the traffic light. We all know that a traffic light has some sequence of light. Maybe this is for stop, this is for walk, and this is, let's say, halt. You may observe this along a pedestrian. So we have stop, walk, and halt, and we have the controller, which is also a saga, and it can be a timer, and the plant will be the light itself. For example, the first light will be stop, the second will be walk, and the third, for example, halt or wait. So because in a crossing, you might observe that this is the crossing and this is for the pedestrian and this is for the vehicle. And there are two sides. One of these light will be pointing in this direction and the other light will be pointing in this direction. So they normally operate in a different state, or we can say opposite state. The input is nothing but a signal for the light that regulates stop in terms of minutes, to walk in terms of the minute, and 3, halt in terms of the minute. So for stop, let's say 30 seconds. To walk, you have 1 minute, and to hold, let's say 15 seconds. So these are the input that is pre-programmed into the controller. So the timing is important in such traffic light, and this circuit will regulate the timing. If in this direction for the pedestrian, if it says stop, then for 30 seconds, for this particular 30 seconds, it will allow the vehicle to pass through while the pedestrian will wait for 30 seconds. And then after the 30 seconds is over, that means this light will be switched off and this light will be switched on. Now people can walk over. And in that case, on the opposite side, it will regulate. If this is for the pedestrian, this will be for the vehicle. And it will operate based on the logic. When this one is off, then this will be on. When this is on, off. After the 1 minute is over, then this will be off and this will be on, and this region will be off and this will be on, allowing the vehicle to pass through. When it comes to an halt, that means when we come across a close approximation where a time normally changes from state from on to off or off to on, there may be 15 seconds delay. That means we must be on hold so that after this there will be a change in the transition. So we can see that the controller is now responsible for controlling these two traffic lights based on the timing that is pre-programmed into the controller. So the timing is now regulated by the controller. So the controller will automatically control the lighting. Therefore, the people and the vehicle must abide by this light. Even when the light for the pedestrian says stop, but someone is walking across the road, then this particular system won't care about this particular person because it won't be able to see the person walking across the street. So these things are pre-programmed. Similar for the vehicle. If the vehicle light says stop while the vehicle is still traveling, then there is no precision, there is no automation in the system. Therefore, we can say we can predict the situation such that we hope that when the light says walk, the people will walk. When the light says stop, the people should not be able to walk. Therefore, this is a direct implication of the open loop system. It doesn't care what is happening. All it follows is the program or the signal input that is pre-programmed into the controller. This is also a good example of an open loop system. But if you want to regulate the system to enable the system to know what is really happening, we can insert a feedback system so that even though the condition is all about having the input signal as an instruction, this particular feedback can override the input signal. If the light says stop and someone is walking, and if the system detects that someone is walking, then it will put a stop for the vehicle to pass through. So we can say that for the output is the vehicle or the people. So if we have a feedback, that means we will normally monitor the vehicle and the people so that the signal input can vary with respect to the actual happenings at the crossing. Another example is the volume control. Imagine we have a radio with a knob which represent the volume. So you can tune your radio from low volume to a high volume. So we can have the input which is the knob and it carries a signal. Imagine when I say signal, you have, let's see, a simple potentiometer as an example, and it is connected to the speaker, and you have the sound that is coming in. And this particular circuit, as an example, in most cases they normally use amplifier as a controller for amplifying the signal. But in case of such example, we can be able to describe it using a potentiometer because it normally increase or decrease the amplitude of a signal. And we we can say the process plant is the speaker, and the output is nothing but the sound itself. So when the knob is 10, it's like we are adjusting the potentiometer or the variable resistor. When we increase or decrease, it will change the amplitude of the sound that is connected to the speaker. In that case, we don't normally care about the output. We all know that by adjusting the sound to the speaker is all we care about. We don't care about what type of disturbance it may require. If we hear that the volume is still low, then we just have to turn the knob. Or if the sound is high, then we can decrease the knob in order to reduce the sound. So in that case, it is a good example of a manual control of a system because we don't need automation. When we talk about automation, that means there must be a feedback that will monitor the sound. If the sound is high, then it will fine tune a controller so that a reasonable signal will be passed through a speaker. But when we deal about manual control, we normally listen. When the sound is high or low, we normally do adjustment as the input from this particular knob. So I think this is also a clear example for you to understand the type of the application in which a open loop control system is used. And finally, a very simple example, an electric bulb. In an electrical bulb, we know a circuit, and we can have some resistor, and we can have the bulb connected to the ground. What can be the input? The input can be the finger, maybe your finger, and the controller can be regarded as the switch, and the plant or the process can be the electric bulb. So the switch will mostly depend on the finger. If you press the switch, then the switch as a controller that will allow the current to pass through to light up this bulb. When you open the switch, that means it will disallow the current to pass through. That means the light bulb will be off. So this is just a simple and simplest example in which it describes the open loop. That means it achieves predictability. That means we predict that by switching the switch to a closed position, the bulb will light. When we open the switch, then the light bulb will be turned off. So it talks about simplicity and cost effective, and it does not care about the disturbance. In case where we say, even though there is light in the room or during the day, it won't care whether there is light in the room or there is no light in the room. All it cares about is when someone is pressing the switch to turn on or turn off the light. Therefore, precision is not too important. We don't care about reliability and automation. Therefore, we normally choose an electric bulb as an open loop system. However, if you like our video, you can kindly subscribe and share with your friends so they can have access to understanding what is a control system and its importance. Now we will move on to the closed loop system.